Hello everyone, today we'll talk about the solution of the problem trapping rainwater 2. And this is a hard problem, it's classified as hard, and indeed I think it's quite challenging. It has a nice short statement. It's essentially a three-dimensional version of a two-dimensional problem. The two-dimensional problem would be essentially on a histogram, so we have some vertical bars equally spaced, and you want to say how much water can be trapped on that two-dimensional image. And here we have a three-dimensional image, so we have a 2D elevation map. For every row and column, we know the height at that position, and we want to know how much water can be trapped within it. And we can, of course, either try from the one-dimensional or two-dimensional, however we want to call it, the lower dimensional version, solve it and generalize it into higher dimensional versions. This is a good idea to do in general if you don't know how to solve the problem. Or we can try to solve this problem immediately starting in 3D. And this is what I'm going to be talking about. Because essentially what we want to do is we want to, for every position on our height map, we want to know the height of the water that's going to be on that position after everything is said and done. And that height can be either equal to the value in height map, which means that there is no water there, or it can be higher, which means that there is some water trapped, and the sum of all those values that are of the differences between the value and the original height is the result. And so we want to know those values. So how do we do it? Well, do we know those values at the beginning for any possible cell? Well, we know it for some cells, because in particular we know it for the boundary of the whole shape. It's very easy to see. For the boundary, there can be no water trapped above any of the boundary cells. If there were some water, that water would just flow over the edge, so there can be no water there. So we have some cells for which we know what the height is going to be. And how do we expand this set? How do we add some new positions for which we can know the height? In general, whenever we have a situation like this, where we have some set for which we know the answer and we want to add some more to that set, this sounds like something like Dijkstra, because the Dijkstra's algorithm on graphs is indeed something that works exactly like this. It just expands and expands the set of nodes for which it knows the result. And the reason why it works is that it uses a priority queue to always select the smallest value from all the values reachable from the current set. And this is going to be very similar to what we are going to be doing here. We're also trying to expand our set starting from the lowest heights. Here's why it works. For instance, at the beginning we have the boundary. So when we look at the smallest height of that boundary, then we know what the height of water is going to be on its neighbor that's within the shape. If that neighbor, of course, exists. Because if it's in a corner, then it doesn't exist. And why do we do it? Well, we know that this neighbor has some height. If it's higher than our boundary cell, then there will be no water on it, because that water would just flow over the boundary cell. But if it's lower than the boundary cell, it'll hold the difference between the heights of water. Why do we have that guarantee? Well, we have that guarantee because there's nowhere for that water to flow over. The first position that we looked at was the lowest position by definition. And in particular, once we have the boundary and the lowest height of the boundary is h, then everything has to be at least equal to h in height, because there will be no possibility for it to flow over either way. Okay, that's easy. So take just the lowest position on the boundary and we can know one more cell. But now notice that that one more cell also creates a boundary for us. We can imagine that its new height is the new boundary that it creates. And that means that we can again look for the smallest cell for which we haven't looked at, and we can update its neighbors by its value. Because again, if their height will be smaller than the height of the node that we're looking at, then they can hold the water equal to the difference, because there is nowhere else that that water could flow over, because otherwise we'd have already found it. We possibly, of course we haven't found it maybe, so in that case we know that they can hold that much water. Or we have already found before that there is some lower boundary, but in that case we are not looking at it again. We are only looking at the node the first time we see it, so the moment that we see it with the lowest possible height. So this is very similar to Dijkstra, and the implementation is actually quite short, because we have some boilerplate, so height and width of the whole map. This edge case, if height or width doesn't exist, is always good to add. We have the boilerplate of directions, so change in row, change in column, pairs of changes. And we're going to be having a priority queue and a set of visited nodes. We start with the boundaries, so we first go over all the rows on the 0th and w minus first columns. We add it to the queue. Likewise for the other direction, so 0th and h minus first row, and columns from 1 to w minus 1, because, well, we could add corners twice, doesn't really matter, but we can also not add them, so we're not adding them here. Of course, we use heap push to maintain PQ, priority queue, as a heap. We have the result, and we just look over all the nodes, and always we take the node for which the height is the smallest we know, because in that case, if that node was not processed yet, and it's the smallest node of all the nodes that are waiting to be processed, we know that there is no lower height that will influence it, because otherwise it would have already been processed. So we take the height, we take the row and column. Of course, we don't want to process it multiple times, so we take it from the priority queue. And now we have the original height, and the height v is the height at which we have reached it. So this is the most limiting height from all the heights from around it. And that difference, if it's positive, if it's negative, we don't want to do anything. If it's positive, we want to add it to the result, so we just max it with 0, add it to the result. And we mark that we have already processed this position. Now we look over the neighbors, so difference in row, difference in column. New row, new column is of course this. If it's not within bounds, we continue. Otherwise, we push it into the queue, and we push it. Of course, it's new row, new column, and the height is the maximum of its height and the height that we have reached our current node with. So a higher node, while it might not hold any water, it might create a higher barrier, a higher boundary for later, so we want to take the maximum here. And at the end, we have the result, which is just the sum over all of those maxes, and this is the final amount of water stored. The final sum over the differences between the height of water on that position and the original height of that position on the elevation map.